30 minutes.
Thank you. Hi everyone, my name is Alejandro Pérez Fernandez. I am a PhD student at the Max Institute for Extraterrestrial Physics. And today the title of my talk is Emulation of Cosmological Simulations using Emulation mapping, which hopefully will make more sense as we go through the slides. This is a work I've been doing in collaboration with Carlos Correa and with my PhD supervisor, Marie Sanchez. So I would like to start by trying to motivate or even care emulating simulations. And I know this is a group of people I don't need to convince of why simulations are so important. So just to name a few things, in cosmology we like simulations because they help us quantify the error bars in our measurements. You need the covariance matrix for the power spectrum. You run a few thousand simulations and you compute your covariance matrix. They give us insight into what different universes with different cosmological parameters might look like. They help us benchmark our theoretical frameworks. You have your EFT power spectrum, you test it against simulations. For example, more recently though, people have started to build emulators for the nonlinear power spectrum, the bispectrum, some summary statistics. And for that, they need simulations. They need a sufficiently large training set. So something that was mentioned already today, simulation-based inference, you might as well use your simulations as your theory itself and don't write down a likelihood or not, and you don't need a covariance matrix because everything is embedded in your simulator. Or some people more recently have been advocating for field-level inference. You might say, okay, if I went through all the trouble of producing new simulations, I might as well use the whole field instead of compressing it. So the problem is that for these three last bullet points, there is a bottleneck, which is the production of the simulations themselves. There is an increasingly high demand for fast production without sacrificing accuracy. And this is the problem we want to solve. So one approach that is what people have been doing also is use perturbation theory. For example, Lagrangian perturbation theory, you have your displacement field, your velocity field, you write down these guys up to the order you want to achieve. Then you write down the kernels analytically, you solve the integrals numerically. But still, you can produce simulations super fast, but still they don't match the embodied simulations at the very nonlinear scales. So in principle, we would like to compromise something that is as good as an LPT simulation, but as accurate as an embodied. And for that, you can use a convolutional neural network. So it would be relatively cheap and still accurate. There is a price to pay though, it doesn't come for free. The price is training, but thankfully or hopefully you only train once, so it's worth the trouble. So this is the general idea. More precisely, what we're using is this architecture. For those of you familiar with machine learning, this is a VNet or a UNet. There are some differences. But this is highly used in image segmentation, for example. And so what we use in images is you have your pixels, and for your pixels, you have channels, your color channels. In this case, instead of pixels, you have voxels, which are your Lagrangian positions. And your channels are your three components of your displacement field and your three components of your velocity field. And then we give this to the network, the input coming from LPT, and we make it learn the 6 output channels that resemble the target, which is an embodied simulation. This is an architecture that was presented already in 2019 in this paper by these people. We only tweaked a few things. And then you want to minimize, of course, a loss function, which it was shown in this other paper that what you want to do is to minimize the resemblance in both Lagrangian and Eulerian space, and this is what we are using. So once you are equipped with a convolutional neural network, you want to build a training set that is optimized or optimal. So you want a training set that is large enough but not too large. And for that, this is where evolution mapping comes into play. So let me talk about a little bit about the linear power spectrum. We know that there are degeneracies. We can separate, the cosmological parameters into two sets. parameters such as the whole dark matter density or the variant density, as well as the spectral tilt, change the shape of the power spectrum only at a given redshift, whereas other parameters as AS, curvature, or the dark energy density change the amplitude only at a given redshift again. Keep in mind that this only holds if you use units in megaparsec instead of megaparsec over h, because h in this case will be a mixture of shape parameters and evolution parameters. So it will obscure these degeneracies that we are interested in. And so since all of these evolution parameters are degenerate, we can compress them in a single parameter, which we choose to be sigma 12, the amplitude of matter fluctuations at scales of 12 megaparsec, not instead of 8 megaparsec over h, because of the reason I just mentioned. So in this sense, your power spectrum at a given redshift for a given set of shape parameters and a given set of evolution parameters will be the same for all of the cases in which you have the same shape parameters and the same sigma 12 at that given redshift as a function of shape and evolution parameters. So this holds perfectly for the linear power spectrum, and you can still use it for the full density and velocity fields. For example, here I have 3 snapshots of a model with this dark energy density, and thus this H value evaluated at different redshifts. And here you can see the sigma 12 values. Then I have another model with the same shape parameters, different dark energy density, and thus a different H. But you can see that if we look at the same sigma 12 values, they basically look the same. Like I can go back and forth, and they are the same by eye. Of course, if you are more picky and you go into the nonlinear scales, you will start noticing differences. And we know how those differences work. We know how to account for them. In Arias' paper of 2022, he explains how to account for them in the nonlinear power spectrum. In Mateo Esposito's paper 2024, how to account for those differences in evolution mapping for the velocity power spectrum. Those won't be relevant in the rest of my talk because at this moment we are not implementing these differences yet, but Andrea will mention them in his talk later. So once we're equipped with both the convolutional neural network and evolution mapping, we build a training set that spans the shape parameters, sigma 12, and 1 evolution parameter, just to give it more freedom. And in this way, we reduce the dimensionality of the training set, because if we wanted to, if we didn't use evolution mapping, then we would have to sample over both shape parameters, evolution parameters, and redshift. And in this case, we are exploiting the fact that we can use sigma 12 as a proxy for the redshift or your time variable. So far, this is the best solution we can train for. And this is because there are memory limits because we are using GPUs. So this is the resolution, a box of 200 megaparsec per side and 128 cubed particles. So this is the 2LPT prediction, the input for the neural network. This is the target, the M body. You can see that they look quite different. 2LPT doesn't have this very nice cosmic wealth. They can very well defined as the M body. And this is what the emulator looks like. So by eye, again, you cannot really tell the difference. Of course, if you zoom in, you will start noticing some differences at the very dense regions. More qualitatively, you can look at the density power spectrum and velocity power spectrum. This is for a fixed cosmology, 25 realizations, the mean and the standard deviation. And you can see that we reach an accuracy of percent levels up to very small scales. Then the next thing you can ask, of course, is how the performance depends on cosmology, which is what I'm showing next. So in this triangle plot, I have evaluated the loss function of a test set that spans all these different cosmological scenarios. And here the loss function, again, is that the lower the better. and here the units don't really matter. And you can see here that if you look at any of these panels there, it's kind of random, right? But if you look at the panel with sigma 12, you'll see this really nice gradient. And it's not really surprising, right? Because like lower values of sigma 12 means there's less clustering. So LQT is already a good prediction. And then higher values, the emulators like struggling a bit more to correct. And then something that we have in the works is how to implement this external information of sigma 12 as part of the information that the CNN takes as input. Because so far the cosmology only comes in the LPT. The neural network doesn't know anything about cosmology. But this is like highly non-trivial to implement, like in general in convolutional neural networks. Something really cool though is that even though we are restricted in the size of the boxes that we can train for, as long as the resolution remains the same, we can reapply what we already trained for larger boxes. For example, here we're going from this resolution, sorry, from these boxes, 200 megaparsec to 800 megaparsec with the same resolution, and we are still able to apply the emulator with no problems. Yeah, in principle, this we did the math and we believe this would be suitable for something like a bus survey volume. Something important, of course, that is what I mentioned in the beginning, is what you want to gain, the wall time. For example, this took 3 hours using 5 nodes on Raven at NCDF, the Max Planck. I forgot what it is. Max Planck Computing and Data Facility. So this is about 1,000 CPU hours, as opposed to this 5 minutes using the quarter of a node, also at Raven, which is 1.5 CPU hours. And this is using CPUs for evaluation. If we make it work on GPUs for evaluating large boxes, then this will take of the order of seconds. So finally, I would like to leave you with my conclusions. And I mean, so yeah, we're trying to build this tool to have kind of on-demand production of simulations. We're exploiting the degeneracies of the cosmological parameters using evolution mapping. This would allow us to, for example, just to name an application, produce covariance matrices for DESI or Euclid for future surveys. And maybe in the future, we might be able to apply this to simulation-based inference and field-level inference. Thank you.
Any questions? Okay.
Sorry, I'm not sure if you mentioned that. Where it will be available?
When? We still don't know. Hopefully by the end of the year.
This year.
This year.
We hope, but
okay.
We do.
Thank you.
So when you train, if I understood correctly, you can ask for different redshift from the machine that you have been training to the data, or it's just
the training set is all at redshift 0, but with different values of sigma 12. So as we are using sigma 12 as our time variable, once everything is put together, when you ask the emulator for a redshift, it will remap it to the corresponding sigma 12. So you don't need, that's why you don't need to train with different redshifts. That's part of the evolution mapping.
Aren't you worried about like some constraints from physics, like the conservation of mass, like continuity equation? That you know, if you generate for closed time steps, you can see if the continuity equation is preserved. But have you thought about such things?
It's something I have discussed with Sophia at some point, and it's something we need to think about a bit carefully. But yeah, that's a good point. Thank you.
Thanks. I appreciate that effort trying to make things more efficient. Could you just explain sort of, or expand on the cost of actually training these, the cost of the training, because and how sure are you that you're only going to do this once? Because in my experience, if you say you're only going to do something once, you're guaranteed to do it 10 times.
Yeah, that's true. Yeah, it took us a while to produce this training set with 2,000 simulations. Actually, we have different different resolutions. And we think we might want to change things a little bit. So we might want to produce a few other training sets also to be sure that these are enough, like this is a large enough training set, maybe 2000 is not enough to the level we want to reach. Because yeah, like as you go to higher values of sigma 12, the performance gets worse. So we want to also correct that. Yeah, it's gonna be a few iterations. It's gonna take choice.
Yeah.
Very nice talk. Have you thought about, so if you were to add a new cosmological parameter, let's say essence into your model, now all of a sudden all your simulations lie on a hypersurface of measure zero in that additional dimensional space. Have you thought about whether how you proceed in such a case where you could sort of have a clever strategy of extent?
So as long as your new parameter is, if your new parameter is an evolution parameter, so if it only changes the amplitude, it's trivial. The problem is if you add a parameter that it changes the shape. And for example, there was a paper extending evolution mapping to include neutrino mass. So yeah, there are ways, but they are not trivial. I think they depend on the parameter.
Thank you.
Okay, I think we don't have enough time. Thank you again.